Mathematicians have a category for structures that defy standard classification: sporadic simple groups. One of the most notoriously complex is the Mathieu group, M24. M24 is an algebraic entity containing hundreds of thousands of symmetrical operations. If you try to hold its raw algebraic form in your mind, the scale is too massive to map. To study an object with this level of complexity, researchers don't start with a massive equation. They start with something small, tangible, and recognizable. They use a standard 4x4 grid, split into contrasting black and white halves. Tracing the history of this 16-square pattern reveals how a basic visual design can serve as a coordinate system for the most complex symmetries in the universe. Humanity has been working with the geometry of this exact grid for thousands of years, long before the existence of formal abstract algebra. Over 2 millennia ago, Plato used a divided diamond figure in the Meno dialogue to explore the philosophical nature of geometric proportions. Artisans independently utilized these mathematical properties, embedding counterchange designs into decorative floor tilings. These diamond geometries were later woven into traditional textiles, passed down through generations of quilters. Because these motifs preserved specific geometric laws, they eventually provided the physical data mathematicians needed to begin mapping multidimensional algebraic space. In the 19th century, mathematicians like Julius Plucker and Felix Klein realized that standard geometry was too limited. To move forward, they shifted their focus from individual points to lines. Klein discovered that an entire line in three-dimensional space could be translated and embedded as a single point resting on a five-dimensional surface, a structure known as the Klein quadric. This meant that basic visual geometry could be used to plot coordinates in higher-dimensional algebraic spaces. In 1952, Hermann Weyl formalized this direction, stating that to understand any structured entity, you must determine its group of automorphisms. This is the complete set of hidden internal symmetries that leave the object's structural relations undisturbed. This created a direct path for researchers. Take a simple geometric object and hunt for its invisible, complex algebraic symmetries. In the 1970s, Stephen H. Cullinane applied Weyl's directive to the ancient diamond patterns found in tile and quilt designs. Cullinane found that this simple grid hides a transformation group consisting of exactly 322,560 distinct operations. This number isn't a coincidence. It perfectly matches the algebraic structure of a four-dimensional linear space over a two-element field. Parallel work by R.T. Curtis took this a step further, connecting these grid symmetries directly to the Mathieu group M24. To handle this connection, Curtis developed the Miracle Octad Generator, or MOG, which is built entirely on these 4x4 arrays. The MOG uses 35 specific configurations of the grid to systematically track and verify the hundreds of thousands of symmetries within M24. By treating the grid as a coordinate system, mathematicians finally had a way to navigate the operations of an algebraic monster through a visual pattern. This historical lineage demonstrates that geometry and algebra are often just different ways of expressing the exact same mathematical properties. We can see this in these 4x4 Latin squares, number-based puzzles that have a direct translation into geometric algebra. Each numeric array on the left corresponds to a specific arrangement of skew lines in projective space, shown in the diagrams on the right. This correspondence allows mathematicians to jump from a visual shape to a numeric calculation without losing any structural information. The result is a system where checking the orientation of a simple pattern allows us to verify properties in dimensions we cannot physically see. This translation is used today in the development of error-correcting codes, which allow for secure digital communication by identifying patterns in corrupted data. It is a core tool in operations research, used to solve complex facility location problems for global logistics. These same symmetries are now being applied to quantum information theory, where they help map the geometry of qubits. The symmetry groups found in an ancient Roman floor mosaic are now used to stabilize quantum computers, protecting fragile information from noise. These everyday symmetrical designs aren't just art. They are the literal blueprints for the algebraic structures that define our universe.